Hello F Sharp. Welcome back. We are continuing our journey of optimizing a topological sort. What we are trying to do is optimize the hottest piece of code in the simulation software I've been working on for my company. Our goal is to be able to sort 1,000 of these graphs in 500 microseconds. Once we're able to do that, we're able to meet the performance requirements of the software that we've been developing, because we want to have a very low latency experience for the people using the software. Now, our initial version took 59 milliseconds, and you can see the results of our optimizations here on the screen. 59 milliseconds is way off the target, but that version was a functionally pure, as simple as you can possibly do translation of the cons algorithm, which is the algorithm we are using for our topological sort. It was the most plain, simple, straightforward translation of that algorithm to a pure functional way of writing it. Now, what we've been doing is we've been profiling and optimizing to try to speed that up. And we've made really significant progress. We are now at just under 1,000 microseconds for 1,000 graphs. So we're getting closer to our target, but we're not quite there. So let's review real quickly what we did last time in order to improve the performance. And last time we were on version 7, and the change we had made is that we had done some profiling and we found, hey, we are creating new objects in this hot loop. And that means we're allocating on the heap, which can incur some garbage collection. And we would rather not do that. So what we did is we created versions of the collections that we were using, the queue and the stack, and we made it stack, which is a stack that is allocated on the stack. And that means instead of allocating on the heap, we're allocating on the stack, and therefore there's no garbage collection. So it is essentially free, not actually free, but free in comparison to allocating on the heap and incurring the garbage collection. So we've made really significant progress, but we still need to go faster. So what do? Well, we don't guess, we measure. And what I did is I went ahead and I went in and I used .trace. There's other tools that you can use to do this. I'm not as familiar with them. In my next series, I'll probably start highlighting how to use those more. But for now, I'm still using .trace because it's the tool I'm most familiar with. And I changed the parameters of this. So now I'm still profiling the same application. I've changed my argument. So now I'm profiling method 7, which was our latest one, and I'm going to perform 10,000 iterations of that to see what is causing it to be slow. And when I do that, this is the result that I get. I'm just saving you time so that you don't have to watch this thing run. It only takes a few seconds, but hey. So I get my main thread, and I go into main profile. Cool, that's the code that we're going to look at, method 7. So this is where I'm starting to get interested. So this is the method that's just being called over and over and over again. And I'm wanting to see what in this method is slow. And when I expand this out, okay, so it's spending most of its time on sort, which makes sense because that is the function that is actually doing the work. And then we see like, hey, it's spending 20% of its time on this invoke, which is likely just a lambda that it's calling in there. There's just a little bit on edge tracker, which is a custom collection that we are using, essentially a bit array for keeping track of things. But there's like nothing in here so far. So what I'm going to do is I'm going to click on sort. And what that does is down here, it tells me what subsystems sort is spending all of its time in. So if I break this down and look in user code, okay, this is my code, and say, hey, I'm running sort. Okay, invoke edge tracker. Okay, this is creating the edge tracker. It's getting the count out of it. It's essentially no time, system code. Okay, it's a little bit of time in the array module where it's creating new arrays, but that's still 1.3%. That's essentially nothing. Move, that's it, copying memory, and barely, like essentially no garbage collection. Well, okay, so this is where I start getting stumped. Like, hey, how do I make this go faster? Because there's no code that is sticking out to me as far as like, oh, this is the code that's slow. Okay, so this is going to be a little harder because it looks like we've hit most of the low hanging fruit, but we still haven't achieved our goal. So we're gonna have to start getting a little creative. Now, if we come back here, where we can look at some of the data that we're getting back from benchmark.net. And I know I've talked about these three columns here: branch instructions, cache misses, and branch misprediction per op. So these are measures of how CPU friendly our code is. I don't know why benchmark.net sometimes shuffle these columns around. It's a little annoying, but whatever. Let's go over it real quickly again. Branch instructions per operation is saying how many branch instructions are in my code per run of this benchmark. Right now there's 1.8 million. Now remember, we're working on 1,000 graphs. So if we want to know how many per graph, we would just divide this number by 1,000. So per graph, so per sort, it looks like there's 1,800 branch instructions. Now that's not necessarily bad because the CPU does a branch prediction. It says like, hey, I think we're going to go this way. I think we're going to go that way. And it will work ahead of you. So just because there's a branch doesn't mean it's strictly bad, because branch predictors are near miraculous pieces of engineering. They're actually not near miraculous. They are extraordinarily well engineered. But what we can see is how many branch mispredictions are happening. And so for 1,000 graphs, we are seeing 78,252 branch mispredictions, or on a per graph basis, 78,000 branch mispredictions. Now, that's less than ideal because whenever the CPU sees a branch, it'll make a guess about which way it thinks it needs to go and start executing down that branch. But if later, when the results of that branch code become available and it's like, oh, you went down the wrong way, all the work that it had done, it has to dump that and basically restart. And because of the way CPUs are designed, that branch misprediction, that being able to do this like speculative computing is a huge performance boost. But whenever it does mispredict, it can cause some serious loss in performance. So an ideal algorithm, well, an ideal case would be like there's no branch misprediction. So this would be 0. So there appears to be some room here. The other thing is this cache misses. Now, our CPUs have multiple levels of cache, and I will try to do some terrible drawing. So in your CPU, you have the core itself, and the core has, so this is like so this is like the ALU. Oh man, this is gonna be rough. I need to get like a Wacom tablet or something. And in here are some registers, and the registers are the things that it is immediately working on. So getting data from a register is instantaneous because it's right there. Now, if what it needs is not in these registers, it will then go to the L1 cache, which is like another set of memory where it can look up values. It's very close. And an L1 cache read is like on the order of like, single digit clock cycles, CPU cycles. If it's not in the L1 cache, then it will go out to L2. The L2 is much larger. It's a much larger pool of memory that it can pull from, but the problem is that it's starting to get much slower. And like an L2 cache read is anywhere from like 15 to I think 30 cycles, depending on your architecture. I'm on a Zen 2, so I think it's like 15 to 20. So ideally, everything you need to work on is in the registers right next to the thing that's actually doing the work. If it's not there, you want it to be in L1, so it's still like really quick for you to get. If it's not there, it's going to look into the L2. I need to do another video, which is just talking about memory architectures, but that will be a really long talk. But if it's not an L2, it might be an L3. And like I said, since I have a Zen 2 processor, it does send an L3 cache. And this is like a much bigger cache than the L2, clearly not to scale. But now the latency is even higher. And then lastly, there is just RAM. There's just RAM way the heck out here. And reading from memory. So let's go back to what cache misses are. So what this is saying, like, hey, when I have a cache miss, it needs a piece of data to continue doing its work. The algorithm, the topological sort, needs a piece of data. It's having to look something up. And what this is telling me is saying, hey, Matthew, I needed something. I looked in L1, it wasn't there. I looked in L2, it wasn't there. I looked in L3, it wasn't there. I had to go all the way out to system memory in order to get it. And the latency of this is huge. Now, again, your CPU is doing everything it can to intelligently load your memory from RAM into caches so that this doesn't happen. But if your working set of memory is large enough, it will saturate your L1, L2, and L3. And so, like, by virtue of the fact that it's too big for your caches, it's going to put it out in system memory. Again, the CPU is trying to be very clever and see, like, hey, what are you likely going to need to work on next? And it will pre-fetch data for you. Now, this is all being hidden from you, but what's important here is for us, when we see like, hey, we have cache misses, this means our topological sort, the CPU is not able to see where we need to go next in terms of what piece of memory we're going to need. And so it is having to go all the way out to system memory. Now, in this case, 73,000 times for 1,000 graphs, which means for each sort of a graph, that's 73 cache misses, approximately 73 cache misses. And this can have massive implications on your performance. And so again, ideally, this would be 0, and that would be like perfect. Now, that's not really realistic. We can probably maybe get it down. We can, how to say this? Because I don't want to like spoilers. I don't want to like give you spoilers at the end, but let's just say getting this number down is really critical. And why am I saying this? So there's a fantastic talk by Fedor Pikus, author of this book, which is a fantastic book. And I'll put a link to a talk that he gave. And he is, I think, the technical, oh man, he's a genius, right? And he works for Mentor. And yeah, his talks are fantastic, brilliant guy. And several of the things that we're going to do later are inspired by things from this book. But in a talk he gave, and I'll find it, put a link in the description, he talked about if you don't have hot code, you likely have hot data. And so your algorithm won't be as fast as you want it to be, and it won't look like any of your code is the thing that is slow, because it's not actually your code that's slow. It's like your memory access pattern that is slow. So what I am seeing when I look at this, when I look at these results from profiling, like I'm not seeing any particular piece of code that is slow. There's nothing that's like saying like, hey, please fix me, which tells me, do I have slow data. And what I mean by that is my data laid out in such a way that my CPU is not able to go faster. So let's look at what our memory layout is for this algorithm. I'm going to come back here to version 7. And I'm going to look at how I have laid out the graph type, because this is what topological sort is doing. It's taking this graph type right here, and it's performing a topological sort on it. So the graph type is made up of sources and targets. Sources and targets are both bars. Now remember, I like units of measure a lot, and if you want to go fast, you want to use raw arrays, but just using raw integers for indexing into your array, like that's fantastic, and that's as fast as you can go, but it's very easy for me, maybe not for you, it's very easy for me to like get confused and get lost of like, okay, which index was that actually intended for? Is that supposed to index to that collection or into that collection? So I like to put units of measure on everything. So it's like, oh, this is an integer and it's really intended for this use. So in this case of indexing, like, oh, this is an index into an array, but it's meant to be of this type. So a bar, in this case, is a read-only wrapper of an array, and the integer that you use to index into it must have the units of node. So, okay, I want to read from an array, I'm using integer, and that integer needs to have a units of node. So you can think of it's just an array with units on the index. And that array is a bunch of references to other arrays. So let's look at this real quick. I'm going to go ahead and clear this. So our graph, let's see if I can do this. So our graph, is that going to work? Oh, come on. Why didn't you stay? I really want this to work because I want to be able to do some more visualization. Okay, cool. So our graph has two fields, which is the sources and the targets. And what those are is saying like, hey, for a given node, what are its sources? So it's pointing at it. And for a node, what are its targets, or like what other nodes are pointing at it? And so I have I have, let's see if I can do this again. I have, come on, you can do it. Text, come on. I have sources and I have targets. And so when I say like, hey, what is sources, right? So let's talk about what that is. So it's an array, right? Here's my array, nice contiguous linear piece of memory. And inside of this array is references. And it's a reference to another array somewhere over here. And that it's probably not that big. Sweet eraser. Okay, that's not going to work. Whatever, it's all good. It's a bunch of references to other arrays which are holding the values that we're interested in. So in the case of sources, I go in and look up for, hey, for node 0, I would come to the first location. That would be a reference to an array somewhere else in the heap to say like, hey, this array now holds the values of the nodes that are actually pointing to that node. Here's the point. What's happening is graph is a reference type. So when it needs to go and get this graph, it's looking up that, it's getting it, and that value is a reference. Well, yep, it's an object. It has two fields, which are sources and targets, which are themselves references to arrays which have values. That array contains references to other arrays. So what's the point of all this? These values, since they're references to other arrays, these values could be spread all over the heap. And so when it's when the topological sort is running, it's having to jump through like, hey, I need sources for this. I'm going to go look up here, and then I'm going to have to go somewhere else on the heap. So this stuff is potentially spread out all over the heap. And so our algorithm is having to jump everywhere all the time. So it doesn't look like any code is slow, because the thing that it's actually waiting on is like, hey, I'm just waiting for memory to load, right? Which is what the cause of all these cache misses is. So what I'm going to do now is I'm going to model this in a different way. I'm going to change it up for version 8, and I'm going to say, well, first of all, I'm going to create a new unit, which is index. And I have the code for creating that, and I want to ensure that it's greater than, it is a non-negative integer, because this is going to be indexing into arrays, and so it makes no sense for it to be negative. Ba-ba-bum. And now I have another type, which is range. And what a range is, it's kind of like a, think of it as like a, it's span-like, and that's like conceptually the same idea as a span, but instead of it like having a pointer to somewhere, it's saying, hey, start at this index, and it's this long, and it's just values. It's not actually pointing to another object or anything like that. So it's saying like, hey, I want a range of something, and you would start at this index and you would go for this long. Okay. And now what I'm going to do, instead of graph being this like array of arrays type of thing, I'm going to have source ranges and source edges. And so if I want to get the sources for a particular node, I would start by getting its range. So for node 0, I would get its range. And that range would say, hey, if you want the edges that are the sources for this node, you would start at this value and you would go this long. And these ranges are ranges of this array that we're wrapping with a bar. And it's saying, hey, these are the edge values. So what does that mean for us? So now, instead of, oh no, I don't want to crop. I really just want to erase a bunch of things. So can I just, sweet. So now, instead of sources and edges, can I not, oh, come on. What I'm going to do is I have source ranges, source edges, target ranges, target edges. Was a little bit embarrassing. I'm going to try this again. So I'm just going to do the sources. Source ranges, source edges. Cool. Now what these are is I have this. No, I just want the brush. I really just want to draw. This is an array of ranges, and this is the array of values. And that's it. It's 2 arrays. So instead of having an array, which then has references to other arrays and potentially having a whole bunch of arrays all spread out everywhere, a graph is just going to be made up of 4 arrays. 2 for the sources and 2 for the targets. So now when the CPU is having to figure out, okay, what data do I need? It's really only concerned with 4 arrays. And that's going to be small enough that that's going to be relatively easy to keep that all in cache. And so we're just reducing the number of things that the CPU is having to go and load data from. Like there's only 4 things to load data from now. So it's more cache friendly. And so when we arrange it like this, and again, the algorithm doesn't really change significantly, but like how we have to look up stuff changes a little bit. But it's much more cache friendly because there's just less things to keep track of, and all the data that we want, we can ensure is kind of nice and contiguous right there together. when we profile that version, we now can sort 1,000 graphs in 681 microseconds. So again, that's about a 28% performance improvement. So that's another big jump. And now we're getting pretty close to our target. We're not quite there, but we're getting near. So what this is, and what's important is I said like, hey, this should be more cache friendly. What absolutely is. We have halved the number of cache misses of our algorithm. And that's just because we're using fewer objects, because we're just saying like, hey, let's just put these things together in packed arrays. And so it's not having to go chasing the heap, just chasing pointers all over the heap. So that reduction in cache misses translates into very significant performance gains. I hope this has been interesting and helpful. I'm still having a lot of fun. I'm looking forward to the next few versions as we continue to push the performance of this. Believe it or not, there's still a lot of performance that we can squeeze out of this. So I'm looking forward to sharing more. If you have any questions, please feel free to leave a comment or to email me. I love talking about this stuff, and I hope that you find this helpful. Thank you for spending a little bit of time with me today. Have a great day. Bye-bye.